Welcome to Digital Arithmetic Operation Circuits Lecture 9 Part 2. Representing sign number using 2's complement. Use the laser pointer. The 2's complement system is used to represent sign number because, as we shall see, it allows us to perform the operation of subtraction by actually performing addition. This is significant because it means that a digital computer can use the same circuitry both to add and to subtract, thereby realizing a saving in the hardware. So this is one of the example what you say. Represent each of the following signed decimal number as a signed binary number in the 2's complement system. Use a total of 5 bits including the sign bit. So including the sign bit there will be 5 bit. Okay. First one is plus 13. So the number is positive. The magnitude is 13 and it will be represented in true magnitude form. So 13 to true magnitude is 110, and this is the binary equivalent true number, true magnitude form. And if we add 0, so this is actually 4 bit 1 2 3 4. If we add 0, this is sign bit due to positive. So this is the representation for this plus 13 using 2's complement system. So for second order it is minus 9, so number is negative. So the magnitude 9 must be represented in 2's complement. So for 9 we know 1001. If you want to do the 2's complement, then you write the complement of each digit. 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0. Add 1 to the least significant digit. So it becomes 0 plus 1, 1, 1 comes here, 1 comes here, 0 comes here. So this is 0, 1, 1, 1. This is 2's complement. So when we attach the sign bit of 1, the complement sign number becomes, so this is sign bit, as it is negative number, so we need to use 1, so it becomes 1 and this number 0 1 1 1 1 0 1 1 1. So this is the representation. The procedure we have just followed requires 2 steps. First we determine the 2's complement of the magnitude, then we have attached the sign bit. This can be accomplished in one single step if we include the sign bit in the 2's complement process. So previously we have written actually 1001 for 9, but if you include the sign bit 0 0 for positive, right, and to the 2's complement we get the 2's complement representation of minus 9 is in a single step, just like here. For 9 we usually write 1001, but if you include the sign 0, so it becomes 01001. Take the complement of this, it becomes 10110. Add 1, so it becomes 10111. So this is basically minus 9, right? So this is just only a single step. We can get the 2's complement of minus 9. Plus 3. So the decimal value is 3 and can be represented in binary using only 2 bit, like 1 1 1 1 is 3. However, the problem statement requires a 4 bit magnitude preceded by a sign bit. So that means in front of 1 1 we need to put 3 more bit to make it 5 bit. So 2 bit 0 0 and another 1 bit for sign bit. As it is plus 3, so we'll put 0. If it is minus 3, we then put 1. So in many situations the number of bits is fixed by the size of the registers that will be holding the binary numbers, so that zeros may have to be added in order to fill the required number of bit positions. Okay, so number D is minus 2. So for Minus 2 start with writing plus 2 using 5 bit. So 2 is 1 0, and if you want to use 5 bit, then it becomes 3 more 0 at the left side. This 0 is for sign bit plus another 2, this normal 0. Take the ones complement. So take the complement of this each bit. 0 becomes 1, 0 becomes 1, 0 becomes 1, 1 becomes 0, 0 becomes 1. Then add 1, the least significant bit, and it becomes this one. So this is the 2's complement representation of minus 2. For plus 8, so 8 is 1000, 1000. To write it using 5 bit, then it becomes, actually it's 4 bit, and for positive sign give 0. And then do the ones complement, take the complement of each bit. 0 becomes 1, 1 becomes 0, 0 becomes 1, 0 becomes 1, 0 becomes 1. Add 1. So 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1. This 1 plus 0, 1, this 1, 1. So this is the 1, 1, 0, 0, 0 is the representation of minus 8, 2's complement representation. Sign extension. This concept is very important. Just look at here. So we use a total of 5 bit to represent the signed numbers. If you look at the previous example, so the size of a register number flip-flop determines the number of binary digits that are stored for each number. Most digital systems today store numbers in registers sized in even multiple of 4 bit. In other words, the storage register will be made up 4, 8, 12, 16, 32, or 64 bit. In a system that stores 8-bit number, 7 bits represents the magnitude and the MSB represents the sign bit. If you want to store a positive 5-bit number in an 8-bit register, it makes sense to simply add leading zeros. The MSB is still 0, indicating a positive value. So positive 9. So positive 9 representation is 1001. It's 5-bit representation, or you can say for positive 9 the sign bit is 0 for 5-bit representation, right? But if you want to store in an 8-bit register, then what will happen this 3-bit? So for positive values we use zeros. So it says MSB is still 0, indicating a positive values. So we add leading zeros. That's what we do. So for the positive value, what would happen for the, so what happens when we try to store 5-bit negative number in an 8-bit register? So in the previous section we found that a 5-bit 2's complement binary representation for minus 9 is 10111, right? This 1 represents the sign bit for minus 9, for minus sign, right? Now if you want to store it in 8-bit register, so this is 5 bits. Other 3 bit, what you will put? Do you put 000? If you put 000, then it will no longer be negative number, right? So we need to put 1 actually instead of 0. So that's what it happens. It says here, if we appended leading zeros, this would no longer be a negative number in 8-bit format. The proper way to extend a negative number is to append leading ones. Thus the value stored for negative 9. So for negative 9, 1 0 1 1 1, right? So the other 3 bit to make it 8 bit will be 1. So this tree is called sign extension to 8-bit format. This one is sign bit and this is 2's complement magnitude. Negation is the operation of converting a positive number to its negative equivalent, or negative number to its positive equivalent. When signed binary numbers are represented in the 2's complement, negation is performed simply by performing the 2's complement operation. To illustrate, let's start with plus 9. The 8-bit binary form, the signed representation is 00001001. If we take 2's complement, it becomes something like that, 11111011, which represents the signed value of minus 9, because this 3 is your, this is your sign bit actually, right? Here sign bit is 11, 1 for minus 9. Likewise, we can start with representation of minus 9, so which is 11110111. Take 2's complement, so it becomes 00001001, which represents plus 9. So these steps are diagram below. So thus we negate a signed binary number by 2's complementing it. This negation changes the number to its equivalent opposite sign. So this is plus 9, 2's complement or negate, this is minus 9. Negate again, get plus 9. This is another example. Each of the following number is a 5-bit signed binary number 2's complement system. Determine the decimal value. So to determine the decimal value. So number A, 01100. So 0 represents is a positive number, right? And for other 4, 1100. So 1100 represents 12. So thus the decimal number is plus 12. The second one, B. So the sign bit is 1 here because the number is 11010. We know that the number is negative, but we cannot tell what the magnitude is. So we can find the magnitude by negating the number to convert it to its positive equivalent. So how we can negate it? Just do the 2's complement. So you got 11010, take the complement, add 1. So this becomes 00110. This is plus 6. So that means it should be minus 6, because the result of the negation is plus 6. Original number 11010 must be equivalent to minus 6. Another example. So it says 10001. Again, this is negative number. We don't really know what the decimal number is. What we can do? 2's complement. So just take the complement of it, add 1. So 01111, it becomes 15. As this is 15, so this one 10001, this is obviously minus 15 by negating. So by negating, you'll get the equivalent positive to negative or negative to positive number. So this is 2's complement representation. Whenever a signed number has 1 in the sign bit, say like for this one, and all other bit are 0, all other bit are 0 for the magnitude bit. Decibel equivalent is minus 2 to the power n, where n is the number of bits in the magnitude. Just look at here, 1, then other bit 0, so it is minus 2 to the power minus 2 to the power n. N is number of bit, sign bit, number of magnitude bit, 1, 2, 3, 3. So it becomes minus 7. So 1, 4, 0. Let's say minus 2 to the power n. N equals 4, 1, 2, 3, 4. Number of bit 16. 1, 5, 0. Minus 0 to the power 5 minus 32, and so on. Notice that it is a special case. Taking the 2's complement of this number produces the value we started with, because we are the negative limit of the range of the numbers that can be represented by these bits.